I came away from this that I'm still very interested in is this idea of creating algorithms that match the stupidity of humans or the genius together, that genius and stupidity. So I have a cognitive map of my house, let's say. I have a cognitive map of my friend's house. These are distinct cognitive maps. The spatial schema is maps of people's houses. What do I expect to have when I arrive in another friend's house, built from those experiences? We ask people, did you grow up in a city or some other situation, suburb, rural, mix? And then we'd simplistically asking with linear models or linear mixed models whether people who grew up in those two different situations navigate differently. Is there a difference? And what we were really shocked when we first looked at the data, or I was shocked, was that...
This is Brain Inspired. I'm Paul. My guest today is Hugo Spiers, who runs the Spiers Lab at University College London. In general, Hugo is interested in understanding spatial cognition, like navigation, in relation to other processes like planning and goal-related behavior, and how brain areas like the hippocampus and prefrontal cortex help coordinate these cognitive functions. So in this episode, we discuss a range of his research and thoughts around those topics. You may have heard about the studies that he's been involved with for years regarding London taxi drivers and how their hippocampus changes as a result of their grueling efforts to memorize how to best navigate London. So we talk about that. We discuss the concept of a schema, which is roughly an abstracted form of knowledge that helps you know how to behave in different environments. Probably the most common example used for a schema is that we all have a schema for eating at a restaurant. Independent of which restaurant we visit, we know about servers and menus and so on. Hugo is interested in spatial schemas for things like navigating a new city you haven't visited before. Hugo also describes his work using reinforcement learning methods to compare how humans and animals solve navigation tasks. And finally, we talk about the video game that he has been using to collect a vast amount of data related to navigation to answer questions like how our navigation ability changes over our lifetimes, the different factors that seem to matter more for our navigation skills, and many other questions. Learn more about Hugo's work through the show notes at braininspired.co/podcast/161. And if you value what I do, you can help me keep doing it by supporting the show in various ways that will cost you very little. Go to braininspired.co to learn more about that. All right, here we go. You caused a little friction in my household recently when I told my kids that there was this new game that they could download and play that they hadn't played yet. We're pretty careful with what they can play, and their screen time is like precious. So any missed opportunities and wasted time doesn't sit very well. And I blamed you because I after learning more about what you're doing, and I came to them and I said, I have this new game, and I think you're really going to enjoy it because they like Minecraft and they like these kinds of things. So I think that they would enjoy navigational games. And of course, I downloaded it. Of course, it didn't work. It asked me for a code. What's going on with that? What am I talking about, first of all, and why can't I play it?
Well, the game I'm guessing you downloaded is called See Your Request.
Yeah.
And the reason you need a code is that we changed over the way that game worked. It was completely open to play in the past, and that meant people could do stuff with it and give us data, but we couldn't tie it to anything else. It was all totally anonymized. So if I wanted to ask you a couple of questions or invite to meet you or anything I wanted to link that to, you couldn't do it. So we set it up with a code. But anyone can get a code off us. They just need to get in touch. If they search See Your Request on the web, they'll find a way to get in touch. And we are looking, I should say, later in this year to change that, though. So that game, I'm sure we'll talk about it at length, but this year we hope to relaunch it. So you do stumble across it. You can play it anonymously and do new things we've never done before with it. So watch this space for some new things we'll be doing.
Yeah, we'll come back to that later. But okay, so is it only researchers that can get access via a code right now, or anyone can?
No, anyone can. Yeah, so there are at least 60 different projects ongoing, all using this code system. So those researchers hand out codes to people, and they contact them, and they get them to do. Typically, they get them to do other things like other tests. They might get them to do running or fill out some other form, questionnaires about their lifestyle, whatever it is those researchers are doing. And then they just tie it back to the code. But the neat thing for us is that code allows the game to work away in the background and send the data directly to a server in a charity. So there's no hit download to send the data to researchers. There's none of that. Yeah, it's working well. Yeah.
Okay. Well, I just wanted to make sure that I started off our conversation with a complaint, and we will come back to Sea Hero Quest in a bit.
Yeah.
You seem busy, and I mean, well, let's start with your origin story, I suppose, because I'm not sure if you've ever had a grant rejected up to this point, but I know you've come in just under the deadline or had very little time to write some grants to study what you want to study. But let's back up even further. I know that you did a PhD with Neil Burgess and John O'Keefe and studying navigation, cognitive maps, etc. Were you always interested? Did you know that that's what you wanted to do from the beginning, or how did you come into thinking that being interested in navigation and cognitive maps and so on?
Yeah, I got interested that during. I decided to do an undergraduate degree in neuroscience when it wasn't sexy. This is back in 1995. I mean, brain's becoming a big story. Like the key book that led me into a lot of this was Francis Crick's book, The Astonishing Hypothesis, where he says we're just a bunch of neurons, and it's a provocative book, and you can take issue with the word "just." By the way, it's a good book, yeah. So I'd started my degree in neuroscience, so I was enjoying it, but I sort of came across all sorts of bits of research and stumbled across all the work on memory, and thought that was amazing. And then what happened to me was probably a lot of other scientists. I decided to do a final thesis project. And I remember going to see Semir Zeki about color vision, and lots of other incredible scientists at that time. But I stumbled across a project that was combining virtual reality, patients who'd had brain surgery, and walking blindfold in the dark experiments at the Institute of Psychiatry, and jumped on this crazy project. It just sounded amazing at the time. And so that's when I first foray into research on cognitive maps and spatial, was with Mike Recce, who, when he was at UCL. He left a while back and has been in the States for some time doing other research. But yeah, that was at that point. That's after that undergraduate project. I got a call from Neil Burgess to say, "Come up to my office." And I thought, "What have I done? What have I done wrong?" It was like the head teacher calling me to their office because I was on his course, and he explained, "No, if you're interested in a PhD, we might." So that was my kind of route in. Yeah.
So the project must have gone well for him to have called you in.
Yeah, it was. He wanted to know all about. He was thinking about doing something similar at that point with patients who'd had. So these are patients who'd had temporal lobe lobectomy, so temporal lobectomies, either in the left or right hemisphere. And back in the sort of late 90s, early 2000s, that was a big, amazing sort of idea of looking at relating brain structure to function. And Neil back then had been hacking away. When I met him, he'd hacked into Duke Nukem. And then started to create this entire virtual town that resulted in a science paper and lots of other papers. But the idea then was to combine that virtual reality game with testing patients. And that's pretty much what I did with John O'Keefe and Neil Burgess as my primary supervisor for 3 years, was putting patients into virtual reality environments. And I kind of not stopped. Still doing that in 2023. Yeah.
I think Duke Nukem has improved. This is a first-person kind of. How would you describe Duke Nukem? It was an early first-person virtual kind of world game, right?
Yeah, it was. I think the thing that was interesting on Duke Nukem was they were like Wolfenstein 3D. There were other games at that time. So it was very soon after they created games you could move in 3D space through on your screen. They were really novel. But that one kind of had more colors, more textures, more variety, and kind of attempted to recreate cinemas, cafes, things in the real world that the other games hadn't done. So it was Neil Burgess spotting that, we could turn this into something that would test real life experiences as it was back then. But it had a lot of violence, monsters, swearing, all that that are in video games. It was not. It definitely wouldn't pass current standards for appropriate video editing.
Yeah, I wasted a lot of time on Duke Nukem, and I'm not a big video game player, but I remember playing that one. Not in a scanner or anything though. So I thought I had heard that you were going along your merry way, and then read about the famous place cells, and that changed your trajectory. And I mean, I don't know if I heard that incorrectly, but then just separately, so correct me if I'm wrong about that. But then even separately, I wonder how many people this happened to, because the idea of discovering these place cells and the idea of there are place cells, and that like gripped people and changed their career paths.
Yeah, I think that has happened. For me, it was grid cells. I've never recorded grid cells, but it was a very similar experience of thinking. Years back, I wondered about doing that and thought I'd probably not cut out for animal research. It's really demanding, and thought, I'll do humans. And then working away in Neil Burgess and John O'Keefe had a kind of joint lab back then. I was constantly exposed to the place cell recording. And it was a really exciting time. Papers were being published every other week, it seemed, major discoveries in that period. But yeah, certainly I can describe a number of other people I've worked with who were doing one thing and then saw the place cells and just dropped everything else, and went to become studying place cells. But yeah, the story of what happened to me was working away. I was in my third postdoc working with Eleanor Maguire, getting to the end of that, thinking of what to do. And I spotted a fellowship the Wellcome Trust had provided, where it would provide you 3 years of funding for retraining, but you had to submit the grant to be successful. You had to show it was the kind of career change where no one would hire you to do this late into your career. So like, you want to learn how to do genetics, but you have no idea how to do it. It was like, you can come and spend time doing that. I don't think they'd factored in people doing single unit recording, because it was like, start doing that and you've only got 3 years, equivalent to a UK PhD. Hard to learn all those techniques when you're late into your career, because you've got other things to juggle. But the key, like you said there with that, was I discovered it was there on a Friday and the deadline was Monday. And so the main thing was you're just getting the finance in order to say, I need finance for 3 years, sort it out. And it got done. I thought it was insane to submit a grant that quick. But it was, a whole weekend planning out 3 years of research and stuff I wasn't doing. So I was very grateful to Kate Jeffrey, who is the PI that helped support me and do that. I joined her lab, but yeah, it was a fantastic thing to be able to do.
Would you recommend waiting until 3 days before? I mean, this kind of procrastination method that like forces you to do the work, Yeah,
no, there is that. I mean, if you're forced against the time wall, then it can focus the mind. But no, it's not an advisable strategy. I also had one other grant where this is a crazy, for me, another crazy story where the James McDonald Foundation got in touch with me on April 1st. I got an email on April 1st, April Fool's Day, saying, "Congratulations, you've been invited to apply for $600,000. All you need to do is," and I think I stopped at the point it said, "all you need to do is," and then they emailed me a week later saying, we emailed you this. We've not had a reply. You've only got 2 weeks to the deadline. Are you sure you don't want to apply?
Wow.
And I realized I'd missed this. So I rapidly put that one together. So yeah, 2 grants where it was very close to the deadline. But yeah, I wouldn't recommend it to people. Do read when someone writes to you saying, "We've got 600,000. It may be true. You never know."
Unless they're a prince. Unless they claim to be a prince, perhaps.
Exactly. Yeah.
So a lot of what you study is navigation, and I know that you love taxi drivers, and you've done a lot of the famous work with taxi drivers who have to learn this. What is it called? The knowledge. Yeah.
The knowledge. Yeah.
Yeah. Quote unquote. Right. Which is like basically how to navigate all of London in the most efficient way possible, and they have to take this super rigorous test before they can become cabbies. Maybe you can just, I know this is like beating a dead horse for you, but maybe you can just describe the kind of the famous findings from those studies. And I don't know where you are, because this was like almost 20 years ago, right? And I don't know where you are, because I know you're doing longitudinal work and studying them as well. So maybe describe those results and then any updates.
Yeah, absolutely. That's been a real joy to work on that project. So the key work with London taxi drivers all goes back to Eleanor Maguire, who's a fellow of the Royal Society at UCL. And I previously worked for 3.5 years with her as my supervisor. So back in 2000, she and others from the brain imaging lab in London, the Phil, as described, the functional imaging lab, had decided this is quite a remarkable group of people. Why don't we scan and measure the structure in their brain, which was a new approach back in 2000, around that time, to measure and use automated systems. But also they looked through each of the scans and measured it. And the reason Eleanor decided to do this was that in a range of other different animals, like food caching birds, squirrels, and some other animals, their hippocampus changes seasonally when they need it to remember things. And the animals that have higher memory demands tend to have a larger hippocampus. So there's reasons across other species to think there would be variation in size. And as you said, taxi drivers on the way in explaining this, their job, like 9 to 5, is solving a spatial navigation problem. That's what they do all day, every day, using their memory. So if you get Uber or some other, they don't do that. They just follow a computer system. But London taxi drivers, the licensed ones, referred to as cabbies, they have this exam to get this little badge to work. And the exam is very simple. It's just ask a set of 10 questions. It's just they're insanely hard. So they'll say things like, right, take me from Berwick Street to Brick Lane. What's every single street between those two very far away points? And if you make a single error, like you go, then they say, no, sorry, you've made a mistake. Come back next time. And so there are about 58,000 streets they could use. So from a computational perspective, it's like a state space of 58,000 states, of which the exam is any 2 random ones. And there's only one solution that they've got to retrieve. So it takes about 4 years. Typically, some can do it in 2 years, but it's often 4 years of study, constant study of the street names. So the knowledge is really that the knowledge is street names. It's not, They need to know other points. So Eleanor found, I keep going back to so this is unusual. What she found was in 2000 that their posterior hippocampus bilaterally was larger than control healthy non-taxi drivers. And the longer they had been taxi drivers cross-sectionally, the larger their posterior hippocampus was. And so when I came in to join this, was that when I joined Eleanor's lab, this is 2003, the aim of one of her grants was let's compare them to bus drivers, because bus drivers do a lot of the same things taxi drivers do. It's just they don't have to remember things. They're just taking the same routes all the time. So it's things like, they're getting visual motion, they're dealing with the pollution, they're having to deal with annoying customers, they live in London, all of these things are controlled for. And there was, as before, a larger posterior hippocampus in taxi drivers compared to bus drivers now. And the longer they had been taxi drivers, the larger their posterior hippocampus was. And then while I was working with Eleanor, we just had to scan them doing their job in an insane study that I wouldn't recommend anyone do. So this is a study we published in 2006 in Neuroimage. And in that study, and I was discussing this with Dick Passingham on email the other day, like Eleanor, I remember the event, she said to me, so how we look at this, she said, why don't you ask them what they're thinking? And I said, what? She said, just ask them what they're thinking. And she had been wondering about this for a while, about the idea that people might actually be able to tell you what's going on. And if you ask people to remember a whole day's experience, it's insane. Of course they can't. They can't do that. But what we did with that experiment was to put the taxi drivers into a £4 million virtual reality simulation that we got our hold of, because it had been built for a video game called The Getaway. And then through extensive, careful work with engineers, rebuilt the Sony PlayStation controller that would pass through a metal detector in an airport undiscovered. But for us, of course, would work inside an MRI scanner. And that was a very hard task. But we then managed to put taxi drivers into a fully detailed simulation of central London with pedestrians, moving traffic, all of it, and hear the voices of people asking them to go to places. And a whole cast of famous neuroscientists were the voices. These were young scientists then, but are now heads of institutes. And, but yeah, no, we after all this painstaking work, after they would do all this driving through London, we sat them down with a biscuit and a cup of tea and said, here's a video replay. What's happening?
Like, what are they thinking?
Yeah, and they can tell you why they made that move. And it was the same with London taxi drivers. They could tell you every reason why, like, I didn't stop to let this guy go by to be nice. I couldn't think about where to go, so I pulled over. Or, oh, I remember seeing Big Ben at that moment. I had eye tracking to verify, are these things they're saying matching up with their eye tracking? 90% of the time they were. It's extremely reliable. But yeah, after all that painstaking work, the only time the hippocampus was interested was the moment they had to first plan. So like the whole rest of the journey to their destination, there was no increased activity in their hippocampus. A bit frustratingly, but that was the result that we uncovered there. And then yeah, that was back in the day. And in recent years, I've decided, well, Eleanor's not done so much more with it. There's a lot more to ask. Why don't we go back and ask taxi drivers some more things? So we've just finished in the last year an fMRI study that's only focused on that moment. So instead of just taking a small sample of events where they have to plan, we now give them like 100 planning events like they do in their exam. And we're scrutinizing the fMRI signal for what's going on and exploiting the advances in computational models for looking at state spaces. And they're planning over a network of spaces, and it's great data. And of course, unsurprisingly, we're measuring the volume of their hippocampus.
Sure.
We don't know yet.
Yeah.
We're still scrutinizing that. So I can't give you a does it replicate 23 years later answer yet, but we hope so.
Are these the same drivers, though, or is it longitudinal in that fashion?
No, this one is cross-sectional again, but we hope we can hang on to these people this time and scan them in another, say, 4 or 5 years' time. Yeah.
Gotcha. Are these drivers paid well?
Yeah, they are.
Okay.
I mean, you get in a London taxi and you want to go 7 minutes, you'll have to fork out like maybe £8. It's not they charge quite a bit to take a fully licensed taxi driver. More expensive than Uber.
Naive question, yeah. I know. But wait, so you were saying that you were asking them, what was the point of asking them what they were thinking? First of all, I mean, while you were saying that, I was thinking my wife is like constantly asking me about my feelings, and I have like no access to that. I can't describe what I'm feeling and thinking at any given moment. So these taxi drivers, although it sounds like what they were describing was more like the reasoning behind their actions, kind of.
It was a bit, yeah. I mean, it was one of those scenarios where if you came back into your house and found like a dog had gone crazy and destroyed, and then there's a vase smashed everywhere, and then you look like a whole sequence of events happen to you like that, and there's a video replay, and you see your face going, like you could walk through what you remember, and you might have, and they had whole sections where they say, I have no memory of this. And they would say, and it would be, I'm just driving down a straight road. There's nothing to see. Yeah. I might have been thinking about tomorrow, whatever, mind wandering, but I don't know what I was thinking. And then they'd turn into a street and they'd say, oh my goodness. And it would look boring to me, but they would say, what's happened to that shop? It's gone. There should be a major, supermarket there, or so they could, anything that was sort of strange. And we simulated one of the worst days you could have in London. So we didn't want to put them through an easy journey. We constantly gave them blocked roads, customers changing their mind, lots of things happening to them. So it created this flow of events and experiences that they were really able to say, that's when I was thinking about this or that. And certainly when they were replanning their route, we would see lots of prefrontal activity. Areas, we know from lots of neuropsychological evidence and others that you would expect to see anterior frontal lobe activity when you have to replan, but just no hippocampus.
So their hippocampus, like their posterior hippocampus, lit up during the before the journey set off, and then it was not active while the journey was happening. But when they had to retool, then it was the frontal cortex that had a higher bold signal.
And if we were to do it again, I'd have measures of how difficult the replanning is, because it's quite possible that maybe if it had been really difficult, then we might have seen the hippocampus involved. That would be my expectation now. Back in 2006, we just had replanning or not replanning, and I think we missed out on. But generally, if it's there, it's only there for some replanning, but not a lot of it. That was my conclusion back then.
This kind of flies in the face of the classic navigational studies in rodents, right? Where the place cell happens when well, in this analog, the place cell would happen when you turned on Fifth Street or something, right? That the place cell would fire, right? And then other place cells would fire in different locations and stuff. But is it, you're recording bold signal, is it that it's just not sensitive enough to pick up the activity, or, could there be that reason?
Yeah, it's a good question. I mean, we have to it's very coarse, right? The bold signal is an indirect measure of the neural activity, that's for sure. And here, when you're thinking about how the place cells would operate typically in a familiar space, pretty much if you looked at rats running through a maze or a box, and one of the most impressive features, and there's a very nice paper by Caswell-Barry's group on the monotonic, like it just maintains the same overall rate of excitation around the entire environment. There's something incredibly beautiful about this homeostatic system that doesn't really go up and down near the edges or the middle. It does something very clever. And so taxi drivers driving through London, you wouldn't actually expect any moment-to-moment changes in the overall bold signal if it's that. Yeah. What you would expect is that if the taxi drivers hit a dead end they weren't expecting and have to now recompute what they're doing, you might well expect sharp wave ripples and to enter into some sort of a non-task focused, a non-stimulus oriented into your own thoughts and planning state, and that you get a lot of sharp wave ripples. And if you're getting sharp wave ripples, you'd expect a lot more bold signal in the hippocampus. So that's, for me, the theoretical link between, we think the hippocampus is involved in doing some memory-based planning through reactivating the maps, recalling the information in those moments. And so I think that's why we saw it at the beginning of the journey, because you have to recall, you're given a street name and you have to retrieve, where is that? How am I going to get there? But for the rest of this, we just don't. That's the link in my mind between what's going on between the neural. But it's speculation. We do need more data. We still need it 2023. Yeah.
Rats are humans. Yeah. I was going to ask you this question, like which is more difficult, right? Recording and planning experiments and so on. But you already alluded to the fact that you did this insane study with humans, and that you wouldn't recommend. So now I was going to guess you're going to say rats were harder to work with, but now I'm going to guess and say humans.
It all depends what you want to get them to do. That is the question. That is the point. What do you want the rats or the humans to do? If you want rats to run around in a box, then they're great. You've got them there. You don't have to invite them in. They're in a research laboratory. But yeah, so the behavior, if you're getting something simple, is fine. Getting rats to do complex planning tasks or something more like humans, that is really hard. And that we had a paper last year in Current Biology where it took a lot, like 5 years, to work up a task that rats really have to think about where they're going to go. That would also be hard for humans. The humans would struggle similarly. So we could try and match rats and humans. And the rat side is much harder than the human side. Dumbing down the human side is making it harder for humans. It's like the other flip side to that. So yeah, but overall rodent research is about 4 or 5 times harder than the human work, I would say.
And so you haven't worked with non-human primates. I know this is an aside. It's probably only of interest to me, but I'm always like questioning, because I worked with non-human primates and I'm always, questioning, like, what would it have been like to be happy, So.
Yeah, no, I haven't, but I can imagine that like 3 or 4 or 5 times harder becomes even harder with non-human primates. Depends what you're trying to do, of course. It's always the issue. Yeah. True.
So, I mean, let's jump into this. I mean, you developed this task, and you already talked about, alluded to the paper that came out last year. And this is specifically to test navigation skills and the neural underpinnings thereof in a setting where rats and humans are doing the same task. So why was that important to do? And then just, tell us about the wonderful successor representation reinforcement learning algorithm that we've talked about a little bit on this show before. But why, what was the question that you're asking? Why was it important to compare rats and humans?
Yeah, no, that's a great question. It seemed to me in the field, we've got lots of research, like review articles and papers sort of trying to combine rodent and human work together and say, oh, look, these tell us about the same sort of things. I just did that with the taxi drivers. I said, I think it's because we see this in rats. It's probably what's happening in humans. But these are, it's always a bit of a marrying up very different scenarios and situations. So we took the view of, what if we were to actually directly link this? So we have rats running the same kind of trajectories that humans would actually run. Would you see similar patterns in their behavior? That was the core question. But the key with that then for me was, if, we often also think about rats and humans as having these different abilities. Like humans have a large prefrontal cortex. And again, I'm just trying to link together these two species. Like how different is their way of navigating, or are they actually quite similar? So one of the core questions in that experiment was, how are they very similar or very different? When we tried to equate, it's always going to be different because you could never quite match it perfectly. But when you really work hard, can you get that? And the answer is yes, there are very similar, rats and humans, in the way they navigate mazes like this. But the other reason to set up this experiment really for me was that then we could test their behavior against models in the maze. We designed this experiment to make a maze that would be useful for testing against reinforcement learning models. So again, in the reinforcement learning field, you talked about a lot in this show. There's fantastic examples of like 4-room mazes where you can look at how applying some hierarchical representation of sub goals, and things in the models really helps improve the match to behavior and things like that people have worked on in reinforcement learning. But I'd known from working in rats from when I'm going back to that training fellowship, of just how hard it is to get rats to do something interesting behaviorally that you can match onto these reinforcement learning. It's amazingly, rats can screw things up in the most amazing, elegant ways you wouldn't believe. They make it hard to run experiments. Like they just get interested in other things. And the key thing you've got to remember is that they've got a fur coat they've got to keep pristine, and they need to go to the toilet. They've got all sorts of other needs. Or like they're prey, they don't want to be eaten. So there are all sorts of things going on that aren't happening for undergraduate students in experiments. And they're quick, they run fast, they like to move quickly. So all these things are going on. But the idea was that if we could build this experiment where you would see comparable behavior, where rats are not succeeding all the time and humans are not succeeding all the time, they're failing, but they're not failing so badly they're lost. So somewhere in between where you've got lots of errors, if they're perfect, you learn nothing. So it took a while to get. And the key innovation in that experiment was having a maze where the rats have to plan and go around obstacles to get to target locations, to get to the goal. But when the maze changes, when you move those obstacles and those barriers, visually there's not a big change. And that's because if you have a big visual change, rats will get confused by where they are and spend time recent marking because they like to pee on things and bite at stuff. So we had these canyons. So it's a maze full of canyons. They run around on this surface trying to get to the target. And we could reconfigure the maze layout to make that happen. And other groups have used similar approaches. John O'Keefe's group, for example, have this honeycomb maze where things move up and down, and ours was much cheaper. We just moved blocks between trials. But it was, I was very pleased by how it worked with the rats. But the other key reason for why you'd want to put rats and humans through the same test is that, yes, you can apply them against the similar reinforcement learning algorithm set. But down the line, as we've done since, you can then apply both the fMRI and the rodent single unit recording or other rodent methods, and then sync these up into the same trajectory space and the same computational model. It seems like quite a powerful idea to have these cross-species methods. Then you can exploit human experiments and rodent experiments in one kind of paradigm. So we're still working on that. That's hard to do as well. But yeah, going back to what you said coming in, we were looking at the rats and humans from the perspective of humans are thinkers. We plan, we mull over what we're going to do. So you might expect humans to fit more with, let's say, a model-based planning system, where you simulate possible trajectories and you choose from a set. And there's wonderful literature in the reinforcement learning field people will be familiar with in model-based reinforcement learning. And you might think rats, having watched them, I have, one of my expectations is they're really they like to build a habit quickly and run. And so it's quite possible that a model-free system that just really emphasizes the optimal actions the rats are taking might capture rats. And then, as you discussed, there's this successor representation model, reinforcement learning model, which was devised by Peter Dayan in 1993. That kind of sat there for a while and became a big thing in the field. But the idea there was that this might be, and Kim Stackenfeld had her paper with sort of prestigious co-authors in Nature Neuroscience, arguing that the hippocampus uses a successor representation from looking at the cells. So again, we wanted to look at that with the data. And Kim Stackenfeld was probably very happy when we found that, yeah, the rats data and the human data, in the way they move, the errors they make, best fit the kind of errors that a successor representation makes. And it's certainly a very sensible system to do this flexible planning, to not have to simulate every single time you move where you might want to go, but to actually just cache a structure of the environment. And so, yeah, it was. But the person who deserves a lot of credit in that project is Will Ducote, who's the first author, who was a PhD student in my lab, who then is now a postdoc in Caswell Barry's lab. And he really threw his heart and soul into all the modeling, helping collect the rodent data, helping with the humans data. It's a hell of a PhD.
What do you think about these different algorithms for example, we'll stick with reinforcement learning algorithms, right? So in like the study, you tested 3 different, very clean algorithms, and then, the successor matched the behavior the best. But as we know, let's say we assume that the brain does this cleanly as well. It has clean systems for, separate systems for successor representation type, for model-based reinforcement learning, and for model-free reinforcement learning. But the reality is, we don't actually know how, separate these systems are in the brain, or really if these clean algorithms map onto anything in the brain, have this like corresponding algorithmic mapping onto processes in the brain. And if they do, they're all interacting, and they're all, would it be fair to say that they're all probably going on at the same time, and then vying for control or being controlled, which one's being used and so on? How do you think about that in terms of like what the results that you got out of that study?
No, that's an excellent perspective. I've given a kind of very basic perspective on that experiment, but you're absolutely right that it doesn't make sense not to do that. So just like in everyday life, if you had to think about it strategically from a model, everything you would do, I need to get the milk from my fridge that I do every day, and I think it's just you would burn out from exhaustion, and you need a lot of glucose for your brain to just do that. So we have to have these habitual systems. And there are other times where, if you can't, your route's blocked, there's a road blockage, or in the real navigating, you can't use your habit system. You're going to have to do something else. So you're right. In the real world, there are all these scenarios where it doesn't make sense that there's one system. There's a lot of evidence these are competing, cooperative, potentially systems for solving problems. And I think maybe one of the ways of looking at our experiment is to say, and this is the challenge of doing the work I do in navigation, is we set up the experiment to test a particular scenario that we thought was interesting. And it probably was oriented towards success with the successor representation approach, in that you had to do flexible planning, but it wasn't pushing you like, my God, you have to rethink everything all the time. So I think that is the context there. And that is the challenge of publishing research papers, is you try and say, we did this work and we think we see this and it makes sense that the successor representation can explain this pattern of phenomenon. It may be used to guide, it may be part of the way we navigate, but you change the paradigm and do something else, you would find very different results. I think there's no question in my mind. But that's an empirical, question, something we need to look at. So I'm not claiming that, it turns out the way we definitely navigate is a successor representation. That would be a very false perspective. And I'm pretty sure we didn't say that in the paper. We had quite a long discussion in there. We tried to our cake and eat it, as I said to someone that wrote to me afterwards. Yeah.
I mean, do you think, though, that something like the successor representation would translate to non-navigational domains in the same proportion? Or, if you made a study and it kind of lended itself toward or was biased toward a successor representation kind of strategy, with the relative different frequencies, let's say of these 3 separate algorithms. I'm sorry, I keep rolling my eyes about these things, but what kind of proportions are we using in our day-to-day lives?
I mean, that comes back to a nasty question again, which is, for each person, what is their daily life? Because some people's lives are really unpredictable. If we take you and me, it's probably a lot of model free. Thank goodness, because again, it's like a super efficient, So I there are beautiful experiments of people taking these models, and when we were looking at our experiment, we weren't at all the first to try this by any means. Nathaniel Dawe had been doing a wonderful job of comparing. You've had him on your show, talking about his wonderful work comparing algorithms to people's behavior. So yeah, this experiment was where, as far as I remember, he hadn't done rats and humans, and we wanted to combine these two literatures together. And I should add, I mean, like, it's not in the paper because it's a very long paper as it is. But when we were trying to create the experiment, it was very hard to get rats to show successful navigation behavior in these mazes, because I was changing the maze around, and they would just keep going down the dead ends or hang around near the goal but not getting to it. So they looked a lot in the early experiments like the model-free algorithms, because we made the mazes so hard that you probably need a lot of model-based planning to solve them, and rats just don't naturally do that. Potentially humans might, but rats certainly weren't. Yeah.
So you said it took like 5 years to get all this working. So was that just titrating for the rats' behavior, or did you have to worry about humans, like making it too easy for humans or anything?
Both the rats are much harder to get that to, and it's all bits projects do just take with different people coming and going, and to building equipment. I had a friend who's an architect design the maze, getting it all. So all those things just take time. So it's not like we were just held to a team of people for 5 years solid. But yeah, the rats just getting a scenario where the rats would run and show these wonderful flexible routes where, for me, the data in that study is beautiful, where I see rats start a journey, they go into the maze, suddenly find that they can't walk towards the goal. They've been doing that again and again. It's blocked. And then use their knowledge to run right around the maze and find their way into the goal where they'd never done it before. So it fit these kind of narratives. Rats don't tend to do that normally, but I think we built up a scenario where they could learn how to do that through the environment we picked. For the humans, it was really hard to reduce. We had to basically put a lot of fog. You need humans in a foggy environment because their vision, we got fantastic binocular vision to spot changes in a maze far away. Once you've got the fog in there, humans become quite dumb like rats. They just don't trying to remember where all these edges in a maze are, and they show the same sort of error patterns.
Dumb like rats. I thought the story was that we're supposed to appreciate animal intelligence a lot more than we do, but you're saying perhaps that's not the case.
Yeah, maybe I'm a bit overly dumb like rats. Like we were trying to get rats to do human things, whereas if the rats had built mazes for us, we'd look like unbelievably dumb. They couldn't believe we couldn't smell the cheese at a distance, So yeah, right. We do have to.
So before we move on, just what's next on that project? I mean, does this tell you anything about the way an AI agent should be built, or how to build intelligent agents, or is it more a story about the nature of our own navigational abilities?
It tells us that last part partly about how what sort of algorithms might explain the way humans would solve a maze in a scenario like this. So that's one framing. But your question about AI, I think, is a good one over what does this tell us about AI and developing those? And you did use a really nice phrase in your say, you took three very clean, for that exact reason, very the simplistically created models we could, with no bells and whistles. We really wanted to have very simple algorithms, see what they did. The takeaway I came away from this that I'm still very interested in is this idea of creating algorithms that match the stupidity of humans or the genius together, that genius and stupidity. A lot of the work, if you look at the beautiful work out of DeepMind that I've been following, because I know that I had my period in Ellen McGuire's lab overlap with Demis Hassabis, so I saw the rise of DeepMind. And a lot of that's incredible, showing these better than the best world chess expert, better than the best Go player now. So we can show AI can do things at a super high level. What I'm quite intrigued by is the idea of building AIs that can simulate dumb people, because there's huge advantages to predicting people being dumb. And I'm sure we'll see more of that work going on, but it's not something I see a lot of. I don't know if you've had guests on your show talking about that, but I don't tend to see a lot of discussion about building AIs to capture stupid behavior, and then what do we do to rule this out or solve it? So I think that's a really nice thing I think we'll see out of some of the, and this project did that. It helped spot, it shows that humans aren't, in this scenario, fantastic model-based planners. They make errors that are not consistent with someone constantly planning. It's not what we do. although some humans in the experiment definitely were, their data matched the model-based plan. So I think that's one of my perspectives on this relation to AI and what's happening in reinforcement learning.
A related topic is ecological validity, right? So there's this craze right now that experiments need to be more ecologically valid. And in a sense, you stripped that away from both the humans and the mice because they have very different affordances in the world. Their umwelts are very different. So an argument could be made, and I'm not trying to be critical. I'm just wondering about your thoughts on this, that by putting rats in taking them out of their ecological environment, taking humans out of their ecological environment, what is really to be gained? Because maybe what you should be doing is putting them both even more so in their ecological environment. But then it's not a controlled, nice experiment where they're doing the same thing, I suppose.
No, so I think that's a lovely question. I think that's great, and I think the answer is that you need a whole range of data, right? So it's great to get fully ethological data on humans and rats where you're looking at what they do. So this was a really nice study, 2021, looking at using Runkeeper, this app for running, where a team in MIT got hold of the data very cleverly through lots of discussions, and were able to show algorithms for how humans making navigational choices in the wild, in their running in like New York. So that's one way of going away from what we're doing that shows you how the behavior in the lab relates to the real world. But another way is, and there's wonderful studies of rats in the real world as well. But then, what's the rationale of bringing this in? And it's exactly that you can't quite so easily get rats running out in the New York subway with optogenetics. People are going to scream. It's not appropriate. It's not ethical to do that. Right? Similarly, recording from people, you can't move MRI scanners currently around. There's movement to do more mobile brain imaging, but they're just methods that mean can't do this. So what can we do? So I think, going back to that, if we had all the best kit and abilities in the world, it would all be out there. But we don't. We need control. We need some lab scenarios, and we don't have the time to collect 1,000 years of data. So I do. I would also say that experiment we ran in the lab, we had humans play a video game that's very much like what millions of people are doing right now. They're playing video games like we did. And the rats, our maze experiment, I think is more ecologically valid than most of the box or plus mazes or thing. It's much more like the kind of scenario you'd find in burrows that rats would crawl through, or it's got that kind of irregular feature layout. So that's my pitch.
I want to come back. Okay, so I know you're doing work recently on schemas, and I realized I don't really know what a schema is, but so we're going to talk about that. And I'll bring in the taxi drivers later in this little conversation, this part of the discussion, I suppose. But in this paper, you distinguish between a spatial schema, cognitive maps, and like event schemas. What is a schema? And do I have it right that are schemas making like a comeback in the neurosciences or in psychological sciences in general, or have they always been there? I see more and more about schemas these days.
Yeah, I mean, they were first brought in. So defining a schema, off the top of my head, I'm sure there's a very nice definition out there on schemas, and it's in our recent Nature Reviews Neuroscience article. I'm sure of that. So in terms of working on schemas, this is the recent paper review I wrote with Shana Rosenbaum and Morris Moscovich, and Della is the first author. She's fantastic. So the team wrote this review on how can we think about distinctions between cognitive maps and schemas. And you're right in the sense that schemas were, as far as I'm aware, going back to Bartlett in the 1930s, psychologists thinking about how you can remember events and things, but actually you abstract over knowledge. So not that you can learn that Paris is the capital of France, this is a semantic fact, but gathering a knowledge base about what's likely to be the case or likely to happen in scenarios. Or if I go into a restaurant, what do I expect to be in restaurants or happen in restaurants? So an event-based schema is things like, what do I expect to happen at birthday parties? So it's not like a semantic fact your brain retrieves and goes, oh, the answer is this. It's a set of predictions, really. So a part of the idea of a schema is predictions, instead of a set of representations, a representation of the brain. Of course, we should run a whole podcast on what representations are, but this idea of something that allows you to map on and have expectations. So the key point in that article we wrote about cognitive maps and spatial schemas is that there's been a lot of talk about event schemas. What do you expect to happen at a birthday party? And less so on what do you expect in a spatial environment, in a city, for example. Although there's been a lot of work on rodents and spatial schemas. And the distinction between the cognitive map and the spatial schema we draw there is that a cognitive map, as described by John O'Keefe and Lynn Nadell in their key book on building on Edward Tolman's famous work on where he proposed cognitive maps, is the idea of an environment. You go into a new environment and you build a internal representation, a map. Doesn't mean it's a vertical map. Some people get really fixated on this. It's what extent it is a map, but it is a system of representations of distances and angles and information about the spatial structure. But it is of that environment. So I have a cognitive map of my house, let's say. I have a cognitive map of my friend's house. These are distinct cognitive maps. The spatial schema is maps of people's houses. What do I expect to have when I arrive in another friend's house, built from those experiences? And what we've pointed out in this article is a surprisingly little known about this. Where is the neural system for the spatial schema really represented? And this is an article in Nature Reviews Neuroscience where the first figure kind of outlines where this may be in the brain. And it's a guess. I would really be honest and say the data is not sufficient to really be confident about where that might be. So with event schemas, so what do I expect at a birthday party? It seems like the ventromedial prefrontal cortex in humans plays an important role in providing that information through neuroimaging data and patients. But for spatial, we don't have as much information. So that's really the key distinction to draw in your mind between a map of an environment you have learned versus a gathering of lots of environments that becomes a schema. And we just link that into lots of ways of thinking about urban analytics. There's been a lot of wonderful work on how we could represent cities and how cities are structured. So it's a wide-ranging review trying to talk to that, but it's something, we still don't know much about. I'd love to know. Extending this to taxi drivers, there was a case when I was working with Eleanor Maguire of an amnesic taxi driver. It's like a Venn diagram of amazing memory, loses memory. Let's study this one person who every 100 years may come forward. And he could navigate a lot of London really well. He could tell you an enormous amount of spatial information. He retained a lot of semantic knowledge about London, and he had a lot of what looked like schematic ways of thinking about the space. It was just when he had to navigate really intricate routes, he couldn't do it. And you definitely wouldn't want to pay him money to take you somewhere in London.
Was he still taxiing?
No, he wasn't. So he was someone you'd shake his hand, say hello, go and get a cup of tea quickly, bring it back, and he would have forgotten who you were and introduce himself again. And when you were navigating, so we used the
classic
big virtual
HM kind of.
Yes, exactly like HM. He had severe bilateral hippocampal damage, and he was densely amnesic, but able to navigate London, a lot of it, but not perfectly. I think, that's the story there from my side.
Yeah. So I'm asking this because after I read your paper on spatial schemas, I read another review, or I think it was a book chapter on schemas, co-written by Alison Preston. Anyway, she like at some point in there's a sentence that says something to the nature of a blah blah blah, a cognitive map which can be considered a spatial schema. So in that sentence, she was like equating spatial schema and cognitive maps. What you're saying is a cognitive map is a specific navigational map, right, to a specific environment, and schemas is an abstraction over many different kinds of environments. Like exactly. In the literature, I don't know what your sense is, but is there agreement on what a schema is? I have trouble conceiving, like, it's so abstract, or is it abstractions, or is it an abstraction? And like, I have trouble visualizing like what a schema actually is and how it will be represented.
No, I think you've got it right. Your confusion is the way you should be if you're reading about this. It's like the reason that's right is that it is confusing. There isn't, so across people, the way they've thought about it and described it gives rise to, because it's not precise. There's not a computational relationship between these things. We can't say this is what you would define for sure as a schema. And in our review, we try to pick up on the fact that we draw examples like, in cities, I expect the big wide streets to be important streets. And I can tell you a lot about what I would, and you can have an awareness and you can describe it, but at a kind of lower level, your brain is just drawing on information to make predictions about where you should go in a space that is building on those learned representations of the environment. So another way of looking at it is that if you were, ideally you'd build a perfect cognitive map. Like you wouldn't make an error ever going in a new place. You go on holiday to the Bahamas. You don't make a single mistake. Whatever you think about the space is perfect. But we're not like that. We do make errors. And part of that might well come because you have a schema of what you expect in the Bahamas and how the streets should be laid out. And it's wrong. Like you think everything should be 90 degrees, all the turns, everything's rectilinear. And it turns out it isn't, and you get caught. So I think that's one of the ways we were thinking about the way in which your prior knowledge, these representations. Other people might say, Hugo's wrong. I don't see them like that. That's not how I think about schemas. And I'd say, that's where we are. It isn't a term that everyone would, I think, agree on. And Ali Preston's comment exactly fits that, where in our review we didn't agree with that. But I wouldn't say there's some huge disagreement with this. I can see where she's coming from.
One of the reasons why I wanted to ask about schemas and bring back the idea of the taxi drivers and the increasing posterior hippocampus is because we think of the brain as hierarchically organized, right? From like lower level kind of details to more abstract concepts to schemas now, right? And in the paper, and I'm going to throw the word gist in here also and ask you what's different. What is a gist relative to a schema? And then how those map onto different parts of the hippocampus. And then you just said schemas are located in, and we'll use this term loosely, ventromedial prefrontal cortex. And you can kind of, I don't know, can you think of that as just higher in the structural hierarchy of the brain, from posterior hippocampus to anterior hippocampus? And then that's the end of the ability of hippocampus, and it needs to offload then on prefrontal cortex. What is that, the idea there?
Yeah. There's a lot going on. You're right. There's certainly lots of evidence that the brain has to have hierarchical structure. There's just anatomically it has. That's not a hard thing to argue. And I think the spatial gist is a bit of that was something we suggested in the article, that you could go to full schema of what do I expect in French cities, right? I go to France, there's particular things to French cities. It's quite a high level representation of my expectations that can go from right at the top, there's a center, there's a cathedral, right down to how the streets are. That's different to other countries. Whereas a spatial gist might be something smaller, we argued, like just fragments of that, where you're capturing commonalities over experiences, say possibly even in a single environment, about the relationships between things. And the confusion here is these things are a bit like they fall between that episodic memory and semantic memory, where you've got one shot, you've experienced this thing, you've encoded the way the park benches were laid out, or you've got a lifetime of knowledge about how park benches are always laid out. And a spatial gist might be somewhere between, in this particular scenario, they tend to be doing this. So it's gathering that kind of a knowledge that's not based on a single episodic event. That might be the spatial gist. Then going into the brain anatomy, I think it's important. There's a lot of debate, as you'll have seen recently, about localist. The anterior hippocampus is doing this function. And you've seen this debate. Yeah. And I fall in the camp of where I think people are talking across as, so for me, there's undoubtedly localization function. Yeah, there has to be. Because of the lower level structures about how we breathe. There are dedicated neurons localized in your brain for allowing me to breathe. Well, for me right now, they're not distributed; they are set there. It's much more complex.
I would hope not.
Complex for the neocortex as to how that's localized. But I think a really key thing is to think about these as the hippocampus does this, and I think it's certainly the case. The neurons are transforming information through the network. And the key thing that keeps coming up again is context, right? So under this, we just talked about it in my mazes, is that's a particular context and experience. So when we say the hippocampus is doing this, it seems like the evidence is that the posterior hippocampus is more engaged in fine-grained detail. There's a very nice review by Lynn Nadell and Morris Moscovich and others, and Jordan Popang, looking at that. So we, in our review, are building on that idea of of more posterior detailed areas to more broad towards the anterior parts. And there's also some evidence in the prefrontal cortex of this. So I think that's where that comes from. But it's important not to think in my mind that it is a localized, it gets passed and then it gets offloaded. And it's much more of a, you're in a particular situation and these circuits will operate, and use the word circuits as in pathways of axons going between neurons. And there's huge feedback and dialogue and a lot of processing going on. But yeah, getting to the bottom of it. But it doesn't mean you can't look and say, where is this tending to happen? Where is this localized to? I think is a reasonable question. It's just how you draw inferences around it. But sorry to go off onto a tangent about the recent
it's
there. Yeah, they keep coming up every so often. Yeah.
I mean, I think, what is it? 99% of scientific disagreements are people talking past each other. It's got to be close to that, right?
Yeah, I thought so. Yeah.
I'm sorry for my naivete about this, but so you brought up like semantic versus episodic memories, right? And does that kind of map on? So semantic is more like generalized knowledge, thought to be, accrued over time via many episodic memories. So in some sense, episodic memories are like the nitty-gritty, detailed navigational memories, like cognitive maps, right? Found that we can kind of localize to the posterior hippocampus. Is there a posterior to anterior, episodic to semantic indexing in the hippocampus as well? Do we know that?
Not that I know of. I don't think people are conceiving it. So it's a really nice question, but I don't think people are conceiving it that way. If they are, I haven't seen that argument made. It's much more. There's lots of different perspectives, of course, and you've had lots of wonderful guests on your program talking about how these things may work. But the impression from a lot of research across the field would be the hippocampus is important for helping you acquire, maintain, and hold on to recent experiences, both the anterior and the posterior. And there's a tendency for the anterior is doing interesting things as well. Like the way it's organized is involved in suppressing. There's a lot of different roles in stress and other functions. It's not just a system purely for spatial memory. That's and certainly in humans. And if you think about the wonderful concept cells, the Halle Berry cells and so on, they're distributed in the hippocampus. So I always think back to that work whenever I'm thinking, I'm well raised in the cognitive map field from John O'Keefe's, UCL perspective. But that is, it's really important to think about those concept cells. So, how the hippocampus is involved in semantic memory is much less clear, I think. But there's the wonderful work from Farineh Varga-Kardem back in 1997 when she discovered that the children with dense amnesia who could learn vast amounts of facts despite not having any episodic memories because they had suffered hippocampal damage at birth or just after. So we do see these amazing dissociations. The system is able to adapt to some things and not others, is telling us something. But yeah, still to this day, I think there's a lot of debate. There's some very interesting reviews out there on how do we think about episodic and semantic memory and how distinct are they really? They are a continuum, there's no doubt. So I think it's rich, interesting to think about these things. Yeah.
Do you think of like a cognitive map to gist to schema? Are those three separate things, or is that a continuum?
Yeah, that would be if you think about it as an active process that you grow up as a person in an environment. So the moment you start moving around, I think would be the experience. You would start to build maps of your environment, right? A cognitive map. But you also start to acquire repeated experiences of what streets tend to be like, how wide they are. So they're constantly, in my mind, going from the point as a child and you're developing your hippocampus and these circuits to help find your way and remember things. In parallel, you'll be building up that type of knowledge. And that happens throughout your whole life, really. And then if you choose a career as an architect, you'll get even better at certain things if you choose a career. So your experiences in life are going to shape the extent to which you construct schemas, from my mind, these expectations, these predictions that your brain has built.
Okay, so this is what I've been wondering about the London taxi driver. Increased posterior hippocampus, And then thinking about if we buy into the idea that the posterior is more concerned with the gritty details, and that as you move more anterior, you are more concerned with more abstractions, higher level concepts, quote unquote. And then I thought, why would I want my posterior hippocampus to be bigger? I would want my anterior hippocampus to be bigger. I should not memorize cities. And that's actually could be detrimental because these taxi drivers also had slightly smaller anterior hippocampi.
Yeah.
And I'm wondering if I don't know what the taxi drivers' IQs are, if there's a correlation to IQ and their ability to pass this test. Like, are low IQs
no, they're
more?
I don't think we've ever had their IQ tested. It would be interesting to do that, but I think they'd be quite high IQ actually. I wouldn't say they'd probably be very typical, but if anything, slightly higher because they spend all their time solving a complex puzzle. But the interesting thing with that, like you just mentioned, they in the early work and replicated, they had a smaller anterior hippocampus, but that replicated with the bus drivers who have the same kind of background of London, same level of education. So I don't think that shrinkage is to do with the other things. It seems to be, I mean, this may relate. I mean, it's in the original article as a suspicion that it's some homeostatic process that, Kevin Mitchell, who's he may well have been on your program. I wouldn't be surprised. Fantastic. He said,
he was.
He said, like, if you keep doing this, surely it's going to, explode out your skull. And it's a tiny change in the size of this, but there may be some conservation that you don't just keep adding here. There's some equilibrium in the distribution in the hippocampus that it's getting altered. We really won't know. I mean, if somebody manages to do a post-mortem collection of taxi driver brains at the end of my life career as a professor, that would be amazing to discover that, but very hard to ethically and chase up and do. I'd still like to know. We still don't know in 2020 to 23 years later. We'd like to find out if we still can replicate that effect, because it may be that it's, for all sorts of reasons, may not still be the case. It has been replicated 3 times, so this is not a result that is just a one-off and in a high-profile journal. It's so we'll find out. I'll let everyone know when we finally get the result.
If I were to force you to answer this, if you could shrink and grow one area of your hippocampus, one region, and grow one region and shrink the other, which would you shrink and which would you grow?
I think I'd go for so I'm thinking back. So I meant to say earlier that the taxi drivers have that shrink. They also are worse at story recall and the ray figure copy, which is you see this abstract picture and you have to copy it out, and then they come back with a blank page 15 minutes later and say, could you redraw that picture you just drew from memory? And they're not clinically bad, they're not impaired, but they're significantly worse than London bus drivers and non-taxi drivers. So if you're going to answer your question, I'm thinking I probably would prefer the detail to be retained, because that's what I do as a scientist. There's a lot of picking through detail than that sort of episodic recall. But my wife might say, you could do with a better episodic memory for what we're supposed to be doing tomorrow. She might have a different.
Yeah. Okay. Well, I mean, first of all, I mentioned IQ earlier, and I probably shouldn't have even said anything, because it's not like IQ is something that we created as a measure of intelligence. But I tend to kind of think that intelligence is correlated with the higher order aspect of thinking, which then would be correlated more with the anterior hippocampus function in this little story that we're telling. But I mean, is that
Yeah, and I think that's a little simplistic in the sense of like you're thinking about how to go back to that model that was provided by Lynn Nadell and Morris Moscovich, kind of like the detail is stored. There's a kind of there's the storage, but the processing of more fine-grained information alongside more global information. And I'm not sure that maps to like the way of creativity or the way you could big picture thinking. I'm not sure it's that just thinking about the kind of evidence, but it is an interesting idea to think, why are some people good at big picture thinking and others too detail focused? Is it to do with the way they're using these circuits? I could be wrong. You could be right. It is something that you could in theory test and find out. Are big creative people, and I do remember like an experiment I would love to run but never got around to, but a famous author, well, at least famous to me, was Will Self, who'd written is an English writer, said his brain was just exhausted with all the detail at the end of finishing a book. It was like burnout for weeks. And he would come back and he said, oh, you've got to scan writers when they finished submitting like a 400-page book because their entire world is in their head. And then a bit like writing a PhD, but somebody's probably going to do that at some point, or may have done it and I missed it. But I think there's some interesting questions there.
Yeah. Well, I mean, I know that the story was like too simplistic, and if you set it up an experiment, it seems rife for, if I did it, it seems rife for just confirming my biases, right? By asking such a simplistic and dumb question, I'm going to get an answer and probably a Nature publication out. No, I'm just kidding. I won't, I'm not going to criticize depending on what I claim, right?
Yeah.
Okay. So what moving forward, like what's the next step in the schema work? Are you testing, how are you testing it? And how are you looking at the nature of the representations that a schema is, or are you?
We're not. I mean, it's a great question. I was involved in that review, and I think we will carry on and do some analysis. The nearest thing to that is our work with the London taxi drivers, looking at how it's not so much one way to look at that is to think London, if you were planning a route through it, you could just plan over all the possible states you've got to go through. Alternatively, you can structure it hierarchically, like this is the area I need to get to. Let's get to the area and then plan within it. And so that gives rise to different predictions in how they plan. And that falls under that kind of schema of how you are representing the structure. So we are we have evidence of that, and we're just writing that up in 2 different manuscripts where we're looking at it. So that's where I think we'll be reporting on something schema-like, which is about the hierarchical structuring of knowledge in London. Yeah.
What's higher than a schema? What's more abstract than a schema? Maybe it's an interesting probing question, so I had to really think about that one. It's from the literature. I don't think anybody's suggesting something. So here I have to make more of a joke about it, I think, than draw on actual art. But when I think about it, it may be your life story. Like, you tell me, who are you? Then it's like, I have to abstract over lots of knowledge. But that's not so much a schema for what to predict, but gathering different bits of all sorts of experiences to explain something. And you have an expectation there of what it is. The schema is, what is that person expecting from me? It's not, when I was 2, this happened to me. A few months later, when I was 2.5, this happened. That's not the level we want. It's identity. It's like
identity. Yeah, your identity of yourself might be higher. But it's a great question.
That. Well done coming up with that. Well done coming up with it so quickly. I didn't have an answer to it, so I like that answer though. Okay, well, my podcasting schema tells me that it's time to move on to Sea Hero Quest. So this is a video game, and we started off talking about it, where the game, someone memorizes a map, and the map has a few locations that they're going to navigate in a little boat to, and it's like a virtual reality kind of game, right? And you had a company help develop the game, and then they advertised, and you had something like 7 billion people play the game, and so something like that, right? Where,
yeah,
I think it's 8 billion, but a lot of people played the game, except my children, and So and then from this game, you've been able to extract lots of different information, even about people's sleeping habits. Why men are so much better at navigating than women. You must have gotten in trouble for having that data come out. So give us the gist of what Sea Hero Quest and what you found so far, and just the power of video games and using video games in scientific inquiry, I suppose.
Yes, I'll start with that maybe. I'll try and give the life story of it in a nutshell, and kind of keep it concise for this story. But yes, the power of games. And I obviously, when I started the podcast, I said I was attracted as an undergraduate to a video game type. I did my PhD with video games. So I've been working for 20 years exploiting video games to put people into situations that allow me to rigorously test. What had happened in around 2015, maybe 2015, I started working with Michael Hornberger, who's a dementia research expert, cognitive expert in dementia. And he runs the Dementia Research Center in UEA, at University of East Anglia. So he and I have been working together. Thinking, could we help develop some diagnostic tools for Alzheimer's, which he's an expert in, involved in video games? But it's really hard to do. And then one day he got an email. Someone contacted him and say, there's a company out there with an unlimited budget who would like to do something like this kind of crazy thing we talked about earlier. And he contacted me and said, I've got this very strange request for a one-page outline for it, probably come to nothing. So we filled it out, helped Michael apply. It went back. And then a couple of months later, he got an email saying, yeah, you've been picked. That's it. We want to work with you to do this thing.
God.
And it was at that point it became apparent that the funder was Deutsche Telekom, or T-Mobile, whose their revenue per annum, their turnover is 68 billion. So they have some money. They're not a poor. They're the richest telecoms company. But their idea was just to take their advertising budget for 1.5 year or whatever it was for a year and do something really innovative. And they employed Saatchi & Saatchi, this creative agency, who are famous in the UK for crazy advertising. Employed them to come up with a way to use the budget. And their idea was, let's make a video game that can do something fun, that gets your message about you care to people. And the idea they picked was dementia, doing something with dementia. And then we got picked, Michael and I, to then create a test that would hopefully help with Alzheimer's. So that's how we got there. It wasn't we got some games designers to come in and, oh, no, it was a funder came to us with a specific project, specifically asking, and we gave them a project. But it was incredible. You know, we got a commercial games company we were able to pick and work with this company, Glitchers, then for a whole year, a high speed developing, less than a year. I think we went from idea to out there to produced, because that's the way a telecoms company would work. But you're right, it's a video game. It was launched in 2016 on the App Store and Google Play, and you play a little boat, and you go around trying to find sea creatures and take photographs of them and share them with your friends. And because it was a telecoms company, you know, we had a good advertising budget to promote it on all sorts of platforms. And one of the key things that budget, after a lot of negotiating from the PR team, was they stalked and tracked down and harassed PewDiePie, the number one YouTuber in the world at that point. I think he still may be the number one YouTuber, but they convinced him to advertise it. And so he pitched on his YouTube channel.
Oh, is this like the where people watch other people play video games?
Exactly. So he's one of those people that plays video games and talks about them and does a lot of other things. But he had 5 million people look at our game in 2 days. So it was an incredible achievement. But he was paid a lot of funding to do that. And he donated all of it to charity, though. So I have to say, very helpful guy and was good in that scenario. But that's some of the background to how we ended up with 4 million people taking part. So we had people from 195 nations enter their data. I mean, you know, and one of the big things you should be asking is like, are we really, you know, did everyone who said they were from the Vatican really from the Vatican? Which we doubt, you know. So this is we're looking forward to publishing an article that's just like, how much bias is there in a data set like this? How do you spot it and what is it? So we've seen the bias in excruciating, fantastic detail, but it's good. Like, it's always there. It's in every lab experiment. You know, if you want to test people in your lab, not everyone's going to come off the street and do your experiment. So I think that's been amazing. But yeah, the game, effectively the game generates time series data. So that was when you said video games for research. A really valuable thing about video games is people will do lots of it. If they enjoy, it's a well-made game, you'll have people and do it in a naturalistic way. And we had the capability with a games company to do that. So people intrinsically wanting to do this, unlike paying them. And the data is really rich. But what I found with the project was that having lots of people play it, you can use the time series of their data, of their trajectory data, to look at things in a lot more detail than you ever could on a normal test that's got a score of 1 to 25 or whatever. And so we've produced quite a lot of papers just looking at the trajectory, like what's the distance people are traveling. So the really good navigators take a short distance, and they tend to be young people in their 20s. In many countries, they tend to be male, and the top place in the world they might come from is Finland, for example. So we're able to look over the data and understand how GDP seems to correlate with performance in our task across the nations. But it's been an absolute joy to look at big data, so you can really screen through it, look at the consistency, and then, be quite robust. You're no longer thinking about p-values. You're just interested in effect size. How much does this matter?
Oh, yeah.
So, for example, we find that left-handers, they navigate maybe differently, but they sleep longer by 1 minute, and it's not a real effect, So the
they
real
sleep
effects.
1 minute longer? Is that what you said?
Somewhere in our data set that I remember thinking I shouldn't. That isn't a correct figure, but there is a sleep. There will be a sleep difference because you measured. We got 700,000 people telling us whether they were left or right-handed, and it will be significant if they sleep half a second longer with 700 data samples. It will be significant, but it's meaningless. Yeah. That's the kind of way of thinking about big data.
One of the stories that you tell is about how people from suburbs tend to navigate better than people from cities, but not just from inner cities, but not just inner cities that are laid out in a very grid-like manner, what you term grittiness, and that. If you live in a city that is really gritty, you're a terrible navigator in Sea Hero Quest. And if you live in a suburb or a city that is less gritty, or something more like Pittsburgh, where I'm going to be soon again, that you tend to be better at navigating. So I don't, flesh that out a little bit more than I just simplistically did. And
that is sort of capturing some of the key result. We published that in Nature in April last year, where the key question we looked at with the data is this very simple. We asked people, did you grow up in a city or some other situation, suburb, rural, mix? And the data clusters, so it's very clear there are people from cities or not cities when you look at the data. And then we'd simplistically asking with linear models or linear mixed models, depending what's in the model, whether people who grew up in those two different situations navigate differently. Is there a difference? And like I said, you can get meaningless, they are, but they're only a little bit better. And what we were really shocked when we first looked at the data, or I was shocked, was that there is quite a reasonable difference. So across the lifespan from, say, early 20s through to late 70s, there's about a 4 to 5 year difference for men and women between people who grew up inside and outside cities, where it's worse growing up inside cities. But if you look at later in life, a woman who grew up, this is on average across all the different nations we looked at, across all the different countries, a woman who grew up outside a city in her 60s is equivalent to a woman who grew up inside a city. So 10-year difference in skill. So for something to moderate your lifespan's ability is pretty shockingly big effect. And then, like you said, that's the average in the world. We found this effect was really big in the USA, but very, very and very overlapping with Argentina. So we're like, why are Argentina and the United States coming out where some other countries are much further down? Why is Ireland far back here? What is it about Ireland? And at that time, we'd seen this geography paper, this analytical paper by Jeff Boeing, went around on Twitter, showing you could measure how gritty every city in the world was using his very simple analysis of the entropy of the streets. If the streets are all lined up, you can measure that mathematically as a highly organized, low entropy system. But if you take somewhere like Sao Paulo, there is no orientation in Sao Paulo. In central Sao Paulo, they all go in different directions. It's highly entropic. And so Antoine Coutreau, who's the first author and spent now 5 years looking at this data with us, initially as a postdoc and then as a PI, he noticed this and said, let's look at that. And lo and behold, there was a very significant correlation across 38 countries between the grittiness of the country's city streets and how badly they were affected by growing up in a city. And so that was the central result in that research paper. Then, of course, to publish it in a highly rigorous journal, you go on a very long journey to do a lot of other things, like show it's not to do with where you live now, test 1,000 other people, replicate the effect. We replicate the effect if you do a driving simulation. So it's not taking a boat around an aquatic environment that gives. But yeah, as you said, like in the game, we can look at the entropy in the game levels. So across 45 levels, we could see that the really, really disorganized levels maximally pull out this disadvantage of growing up in, say, Chicago. So if someone from Chicago is going to find those much harder. But the title of the paper is not "Cities are bad for your navigation." That's not what the title of the paper is. It's, I forget the exact title, but it's like "Entropy shapes your future spatial ability," because we found that in the really gritty levels in Sea Hero Quest, people from gritty cities actually had a slight advantage, although there's a somewhat of an overlap with non-city people. So it's not that so that goes back to the schemas. So it seems that people who grow up in city environments have an expectation of what they expect to see when they navigate a world, and it biases them. So that's the real. There's a lot of peripheral and loads of endless supplemental figures in that paper to ram home the point and take it apart. And we had 5 reviewers who asked a lot of questions about that data.
Oh, wow.
It made a much better paper. Yeah. Yeah. The editor apologized. She said, "Very sorry, but we've given you 5 reviewers to make sure every single one of them is happy before we publish this."
Oh my God. But is there you were saying that, there's not a story to be told necessarily of like where you should grow up or something. No. And you were mentioning, with such a large data set, you're going to get good p-values. Well, you're going to get effects. Just the question is like how large those effects are. But then the question is, even if those effects are kind of large, like, do I care? Why do I care about whether I can navigate, like for my real world experience moving through the world, like just because I can't get around quite as well in a city, does that mean, do I really need to worry about that? How much should I worry about it?
I wouldn't worry about that. I mean, I think if you look at clinical issues, surgeons doing neurosurgery are not that worried about you losing your spatial skill. That they might tamper with your language ability, they're terrified, right? So that is a known fact for neurosurgery. You do not want to damage the language. So I think that's here. I agree. I think it's fascinating, and it's one of the few studies in the world where we've looked at how some experiences in childhood are then shaping your future experiences later. It's very hard to study these on a mass scale, but we would assume that it's likely in areas like language and other aspects of how it's affected. But yeah, we shouldn't worry about it, I don't think. I think the only thing there is I was really surprised, like I said, this 10-year difference. And if you think you're losing this skill, it's like, well, there is a clear advantage. And as Antoine said to me once, mulling over the data, it's like, well, does it matter growing up in a gritty city? Well, it turns out most of the world is not gritty. So you are kind of in a disadvantage. So it is better probably to grow up outside cities and get that experience on average.
So in the United States anyway, I guess people who voted for Trump are really good at navigating, and people who voted Democrat maybe aren't as good at navigating. I hadn't thought about this before, and I'm apologize if you are doing this work and I just overlooked it already. But are you training reinforcement learning agents to play Sea Hero Quest also, and then comparing that, like different kinds of reinforcement learning algorithms to the different developmental stages of humans, et cetera, and how they navigate?
No, it's really nice you raised that, because we have thought about that and we've looked into it. We've recently got more funding to do things like that. But actually, that's a good example where somebody listening to your podcast might be interested in this and get in touch, because the data is so rich and so large that there's really good scope for collaborators to join and do things. We do have 3 teams playing with the data. Every single group who comes to do something with the data will see it differently and have their own questions. So we haven't tried kind of building reinforcement learning agents to do that, to play the game, but it is plausible. It's a very interesting angle. And if anybody is interested, I mean, I should also take this point to pitch, and hopefully on the website, maybe we'll put some details where the game is totally free for people to use for research. There's no cost or anything. It's completely set up to maximum. There's 60 projects, but also the data is completely accessible. Everything we've done with it, someone can download. And we'd be delighted to kind of facilitate someone doing something with this data. So it's hopefully more people will do things with this data, and we'd love to speak to them to help them do it.
Do you have like a ton of other, like, I know that one of the things that you were interested in was sleep. Why were you interested in sleep? And then, of course, the robust finding is that 7 hours is the perfect amount of sleep for navigation, right?
That's right. So this is our Nature Communications article end of last year. Yeah. So when we set up, I should say, the data looks really rich, right? And it is rich spatially. We have wonderful time series and 4 million people. But maybe 70% or less fill out all these demographic questions. And working on the project, we had a lot of fight with the developers and the team, but they said, you really can't ask more than 9 questions. People are not going to answer. I think they might have, but their criteria as well was not only we wouldn't ask loads of questions, but it was these have to translate into 17 languages and be iconic. You can just click and understand. And so sleep is an easy one to say, how many hours of sleep do you typically get? But it is also related to sleep disruption and Alzheimer's. So a lot of our questions were kind of, would this help in refining the data? But it's a great question. And yeah, like you said, what we found was that later in life, right, so after the age, after your early 50s through to 70, people who report 7 hours are better navigators than people who report 8, 9, or any other range. Doesn't recommend you should sleep 7 hours. It's just the people who tell you that they sleep 7 hours tend to perform better. So you can make that causal relationship and say it is good to get 7 hours, but the data by itself doesn't provide the direct evidence for that. But yeah, I was really struck. It wasn't, and the key exciting thing I saw in that data set with the sleep data was observing a pattern no one had seen before. So it's not too surprising that getting optimal sleep might help your cognitive skill. But what we hadn't known until that paper was that if you look across the lifespan for reported sleep, it's not smooth. There's something happening to humans that between the age of early life through the end of your teenage years to 33, it declines. You get less and less. Probably when you've got children, it's really low and plateaus. And then after 53, it goes higher again. So it's not a smooth U shape. And we don't know why. We say in the article, we don't know why those particular age bands are fixed like this. But the amazing thing for us was when you separate the data set in half and just say, we'll look at men and we'll look at women, you think these numbers are going to change. And they didn't. 33, 53 for both men and women. And you say, well, take all the Western people who've got the high GDP countries who are all living in like rich scenarios with loads of facilities and play video games, and these group, maybe they'll have different numbers to the people in low and middle income countries. No, same numbers again, 33 and 53. So there's something going on with the human lifespan and sleep around 33 and 53 on average that we don't know why. So maybe at the end of my career, someone will answer me and say, you know what it is. I don't know the moment.
By then you'll be sleeping more.
I hope so. That's what the data suggests.
Yeah. I know it's 10 p.m. in your world, and your children have slept through this whole thing. Yeah, thank you for that. We got lucky. But you got to get some sleep, even though you're at that stage of your life where you don't get any sleep. Yeah. You still need a little sleep. So I appreciate you staying up so late to talk to me and finally doing this with me. We've had to reschedule a few times, and so thanks.
Oh, no problem. It's been a pleasure. I've been really enjoying your podcast for years now. And it's a real delight to finally make it after scheduling onto this. So I really appreciate you taking the time to talk to me. And I'll continue to enjoy your podcast going forward, I'm sure. It's a fantastic range of guests you've had. So great. And you've asked me fantastic questions that other podcasters don't ask. And it's great. Really appreciate it.
I alone produce Brain Inspired. If you value this podcast, consider supporting it through Patreon to access full versions of all the episodes and to join our Discord community. Or if you want to learn more about the intersection of neuroscience and AI, consider signing up for my online course, Neuro AI, The Quest to Explain Intelligence. Go to braininspired.co to learn more. To get in touch with me, email paul@braininspired.co. You're hearing music by The New Year. find them at thenewyear.net. Thank you for your support. See you next time.